Hello there. I'm delighted you found your way here tonight. Whether you're tucked beneath warm blankets, curled up on a comfortable sofa, or simply seeking a moment of calm after a long day, you're in exactly the right place. Tonight, we're embarking on a gentle journey into one of the most remarkable defense systems ever devised, not by any human engineer or military strategist, but by your own body. We're going to explore the fascinating world of antibodies, those microscopic guardians that patrol your bloodstream like tiny, vigilant sentries. Now, I should offer a small warning. While this video is crafted to help you unwind and drift peacefully towards sleep, there's always the possibility that the story of these cellular defenders might prove just captivating enough to keep you listening. But if you do find yourself wide awake at midnight, marveling at the elegance of your immune system, well, at least you'll have gained some wonderful insights into the remarkable machinery working silently within you. Before we begin our quiet exploration, I'd love to know where in the world are you listening from tonight, and what time is it in your corner of the universe? Are you settling in for the evening in Edinburgh, perhaps catching this during a lunch break in Los Angeles, or maybe it's the small hours of the morning in Tokyo? Wherever you are, whatever the hour, you're most welcome here. If you find these gentle scientific journeys helpful for relaxation, please consider giving this video a like and subscribing to the channel. It helps other curious minds discover this peaceful corner of learning. And just a gentle reminder, while we'll be discussing how your body's defense systems work, this video is purely for educational and relaxation purposes. It's not intended as medical advice or a substitute for professional healthcare. If you have any health concerns or questions about your immune system, please consult with a qualified medical professional. So, take a slow, deep breath, let your shoulders drop, close your eyes if you'd like. Tonight, we're going to discover how your body has been protecting you every single day since you were born, with an army of defenders so small you could fit millions of them on the head of a pin, yet so sophisticated they would make the most advanced security system look primitive by comparison. Picture this. Right now, as you listen to my voice, there's an invisible war being waged inside you. Not a violent, destructive conflict, but rather an elegant dance of protection and recognition. Microscopic invaders, bacteria, viruses, toxins are constantly attempting to breach your body's defenses. And standing guard against this endless tide of potential threats are your antibodies, those remarkable molecular soldiers we're about to meet. But what exactly is an antibody? Imagine, if you will, a master key that's been specially crafted to fit one specific lock. Now imagine that this key is alive, intelligent in its own way, and capable of seeking out its matching lock among millions of others. That's essentially what an antibody does. It's a Y-shaped protein that has been custom designed by your immune system to recognize and neutralize one particular type of threat. These tiny defenders are also known as immunoglobulins, a rather grand name that simply means immune proteins. They float through your bloodstream and lymphatic system like microscopic patrol boats, each one carrying a unique molecular fingerprint that allows it to identify its specific target. Some antibodies are designed to recognize the surface proteins of the flu virus, others to identify bacterial toxins, and still others to flag allergens or other foreign substances. The story of how we discovered these cellular guardians is quite remarkable in itself. Back in the late 1800s, scientists were just beginning to understand that our bodies had ways of fighting off disease. A German physician named Emil von Behring was working with diphtheria, a terrible bacterial infection that was claiming thousands of children's lives each year. He noticed something peculiar. Animals that had survived the disease seemed to have something in their blood that could protect other animals from the same infection. Behring discovered that he could transfer this protection by injecting the blood serum from recovered animals into healthy ones. He called these mysterious protective substances antitoxins, though he had no idea what they actually were. What he had stumbled upon, of course, were antibodies, though it would be decades before scientists understood their true nature and structure. It wasn't until the 1952nd that researchers finally got their first clear look at an antibody. Using the newly developed technique of X-ray crystallography, they could see that these molecular defenders had a distinctive Y shape, rather like a tiny wishbone. This shape isn't accidental. It's perfectly designed for the antibody's dual purpose of recognition and destruction. The two upper arms of the Y contain the business end of the antibody, the antigen binding sites. These are the parts that actually recognize and latch onto foreign invaders. Think of them as the antibody's hands, each one shaped to grip a specific molecular target with exquisite precision. The stem of the Y, meanwhile, acts as a signal flag, alerting other parts of your immune system that a threat has been identified and tagged for elimination. But here's where the story becomes truly extraordinary. Your body can produce antibodies against threats it has never encountered before. This isn't magic, it's the result of one of the most sophisticated biological systems ever discovered. Your immune system maintains a vast library of genetic templates, like a molecular cookbook containing recipes for millions of different antibodies. When a new threat appears, your body can quickly flip through this cookbook, find the right recipe, and begin mass-producing the appropriate antibodies. This process begins in your bone marrow, in specialized cells called B lymphocytes, or B cells for short. Each B cell is like a tiny factory that has been pre-programmed to produce one specific type of antibody. When a B cell encounters the antigen, the foreign substance that matches its particular antibody, it's like a lock clicking open. The B cell becomes activated and begins to divide rapidly, creating an army of identical cells, all churning out the same antibody. Within days, what started as a single B cell can give rise to thousands of plasma cells, each one a dedicated antibody factory. These plasma cells are remarkable in their single-minded devotion to their task. They sacrifice almost everything else to focus on antibody production. Their cellular machinery becomes so specialized for manufacturing antibodies that they can produce and secrete thousands of these molecular defenders every second. But the truly elegant part of this system is what happens after the immediate threat has been dealt with. Most of the plasma cells die off once they're no longer needed, but a few transform into something special: memory B cells. These are like your immune system's librarians, quietly filing away the information about this particular threat for future reference. Memory B cells can survive for decades, sometimes for your entire lifetime, ready to spring into action if the same invader ever dares to return. This is why you typically only get certain diseases once. The first time your body encounters measles or mumps, it takes several days to mount an effective antibody response. But if you're exposed to the same virus years later, those memory B cells recognize the threat immediately and begin producing antibodies within hours. It's a biological early warning system of breathtaking sophistication. The structure of antibodies themselves is a marvel of molecular engineering. Each one consists of 4 protein chains, 2 heavy chains, and 2 light chains held together by chemical bonds called disulfide bridges. These chains fold and twist into the characteristic Y shape, creating a molecule that's both flexible enough to navigate through your bloodstream and rigid enough to maintain its specific binding properties. At the tips of the Y-shaped molecule lie the antigen binding sites, and this is where the real magic happens. These sites are created by the variable regions of the antibody sections of the protein that can be shuffled and recombined in countless different ways. It's rather like having a molecular Lego set where the same basic building blocks can be assembled into millions of different configurations, each one designed to recognize a different target. The precision of this molecular recognition is almost impossible to comprehend. An antibody designed to bind to a specific protein on the surface of a virus can distinguish that protein from thousands of other, very similar proteins in your body. It's like having a lock that's so precisely crafted that it will only open for one specific key, even when that key differs from all the others by just a few molecular bumps and grooves. Now, You might wonder how your body knows what constitutes a threat in the first place. After all, you're constantly exposed to harmless substances, the proteins in your food, the dust motes floating through the air, the countless microorganisms that live peacefully on your skin. How does your immune system distinguish between what's dangerous and what's benign? This is one of immunology's most fascinating puzzles, and the answer lies in a concept called self versus non-self recognition. During the development of your immune system, particularly in the early weeks and months of life, your B cells undergo a rigorous education process. Those that produce antibodies against your own tissues are eliminated or rendered inactive, a process called tolerance induction. What remains is a population of B cells that will only respond to foreign substances. But this system isn't perfect, and sometimes it goes awry. When antibodies mistakenly target your body's own tissues, the result is an autoimmune disease. Conditions like rheumatoid arthritis, type 1 diabetes, and multiple sclerosis all involve antibodies that have, in essence, turned against their own side. It's like having security guards who've forgotten how to distinguish between residents and intruders. On the other end of the spectrum, sometimes the antibody response can be too enthusiastic, reacting to harmless substances like pollen, pet dander, or certain foods. These are the antibodies responsible for allergies, and they represent a case where your immune system's protective instincts have become overprotective. The antibodies involved in allergic reactions, called IgE antibodies, trigger the release of histamine and other inflammatory substances, leading to the familiar symptoms of sneezing, itching, and swelling. Speaking of different types of antibodies, your body actually produces several distinct classes, each specialized for different types of threats and different parts of your anatomy. The most common type in your bloodstream is called IgG. These are your body's general-purpose antibodies, the versatile foot soldiers of your immune system. They can cross the placental barrier during pregnancy, providing newborn babies with temporary protection against diseases their mothers have encountered. Then there's IgM, typically the first antibody produced when you encounter a new threat. These antibodies are larger and more powerful than IgG, designed for the initial assault against invaders. IgA antibodies patrol your mucous membranes, the moist surfaces of your respiratory and digestive tracts, where many pathogens first attempt to gain entry. And IgE, as we mentioned, is the antibody class associated with allergic reactions and responses to parasitic infections. The production of these different antibody types is carefully orchestrated by other cells in your immune system, particularly helper T cells. These cellular conductors help coordinate the immune response, determining not just whether antibodies should be produced, but what type would be most appropriate for the specific threat at hand. It's a level of coordination that would make any military strategist envious. But perhaps the most remarkable thing about antibodies is their sheer diversity. Scientists estimate that your body is capable of producing somewhere between 10 billion and 100 billion different antibodies, more than there are stars in our galaxy. This staggering variety is achieved through a process called somatic hypermutation, where the genes encoding antibodies undergo rapid, controlled changes, creating new variants that might bind even more effectively to their targets. It's as if your immune system is constantly running a molecular evolution experiment, testing new antibody designs and keeping the ones that work best. This process means that your antibodies don't just recognize threats, they actually get better at recognizing them over time, fine-tuning their molecular grip with each encounter. As you lie there tonight, perhaps feeling drowsy as these microscopic marvels work their silent magic, remember that this extraordinary system has been protecting you since before you took your first breath. The antibodies circulating through your bloodstream right now represent millions of years of evolutionary refinement, a biological masterpiece that continues to adapt and improve with every challenge it faces. And we've only just begun to explore this fascinating world. In our next chapter, we'll delve deeper into how these molecular defenders actually neutralize their targets, the elegant ways they communicate with other parts of your immune system, and the remarkable stories of how scientists have learned to harness their power to create life-saving treatments and vaccines. But for now, as the gentle rhythm of your breathing slows and your thoughts begin to drift, take comfort in knowing that you are protected by one of nature's most sophisticated defense systems, an army of tiny guardians, each one perfectly crafted, endlessly vigilant, and utterly devoted to keeping you safe. The antibodies we've been gently exploring have many ways of carrying out their protective mission, each method as elegant as it is effective. Think of them as having a toolkit of strategies, rather like a skilled craftsperson who knows exactly which tool to use for each particular task. The beauty lies not just in their individual capabilities, but in how they work together as part of a larger, harmonious system. When an antibody encounters its target, let's say a virus, attempting to invade one of your cells, the first thing it does is bind to it. This binding isn't a violent collision, but rather more like two puzzle pieces finding their perfect fit. The antibody wraps around specific proteins on the virus's surface, rather like a molecular embrace. This binding serves several purposes, the first being simple interference. By coating the virus with antibodies, your body essentially blindfolds the invader, preventing it from recognizing and attaching to your healthy cells. Imagine a burglar trying to pick a lock, only to find that someone has filled the keyhole with clay. The virus, now covered in antibodies, simply can't find the cellular doorways it needs to begin an infection. This process, called neutralization, is one of the most straightforward yet effective strategies in your immune system's playbook. But neutralization is just the beginning. Once antibodies have tagged a threat, they become like molecular lighthouses, broadcasting signals to other parts of your immune system. The stem portion of the Y-shaped antibody, what scientists call the FC region, acts as a beacon, attracting specialized immune cells that are always on patrol through your tissues and bloodstream. One type of these cellular responders is the macrophage, whose name literally means big eater. These are the garbage collectors of your immune system, capable of engulfing and digesting anything that's been marked by antibodies. When a macrophage encounters a virus or bacterium decorated with antibodies, it's like seeing a "please dispose of me" sign written in a language only immune cells can read. The macrophage promptly swallows the tagged invader whole, breaking it down into harmless components that can be safely recycled by your body. Another type of responder is the natural killer cell. Despite its rather dramatic name, performs its duties with quiet efficiency. These cells are particularly good at dealing with your own cells that have become infected or corrupted. When antibodies mark an infected cell, natural killer cells can recognize the signal and eliminate the compromised cell before it can spread the infection to its neighbors. It's a harsh but necessary sacrifice, rather like removing a few damaged boards to save an entire ship. The coordination between antibodies and these cellular partners is achieved through a process called opsonization, a word that comes from the Greek term meaning to prepare food. Just as a chef might season and prepare ingredients before cooking, antibodies prepare pathogens for consumption by immune cells. They coat the surface of bacteria and viruses with molecular signals that make these invaders irresistibly appetizing to macrophages and other cellular defenders. But the antibody system has even more sophisticated strategies at its disposal. One of the most elegant is called complement activation. The complement system consists of about 30 different proteins that normally float inactively through your bloodstream, rather like a disassembled molecular machine waiting for the right signal to spring into action. When antibodies bind to a pathogen, they can trigger a cascade of complement activation that's both beautiful and deadly, at least from the pathogen's perspective. This complement cascade is like a carefully choreographed domino effect. Once the first complement protein is activated by the antibody, it activates the next protein in the sequence, which activates the next, and so on. The end result is the formation of what's called the membrane attack complex, a ring-shaped structure that punches holes directly through the outer membrane of bacteria. It's molecular warfare, at its most precise, creating pores that cause the bacterial cell to leak its contents and die. The complement system can also enhance the work of immune cells by creating powerful chemical attractants. When complement proteins are activated, they release molecular signals that act like distress flares, summoning more immune cells to the site of infection. It's as if the antibodies are not only fighting the invaders directly, but also calling for reinforcements, ensuring that help arrives exactly where and when it's needed. Now, you might wonder how your body manages to produce such a diverse array of antibodies without overwhelming its own resources. The answer lies in one of biology's most ingenious solutions, the concept of clonal selection. Remember those B cells we discussed earlier, each one programmed to produce a specific antibody? Well, your body maintains millions of these B cells, each carrying a different antibody recipe, but keeping most of them in a resting state. Think of it as maintaining a vast library where most of the books remain on the shelves, unopened and undisturbed, until someone needs the specific information they contain. When a pathogen enters your body, it's like a librarian searching through millions of volumes to find the exact book that contains the information needed to solve a particular problem. Once the right B cell has found the one whose antibody can bind to this specific invader, it's as if that book suddenly starts reproducing itself, creating thousands of copies to meet the immediate demand. This system is remarkably efficient because it allows your body to maintain the potential to respond to virtually any threat without wasting energy producing antibodies for threats that may never materialize. It's like having a vast army in reserve, with only the needed troops being called to active duty when a specific battle requires their particular skills. The process of clonal selection also explains why your immune response gets stronger with repeated exposure to the same pathogen. Each time your body encounters a familiar threat, the memory B cells we discussed earlier don't just produce the same antibodies, they actually produce improved versions. Through a process called affinity maturation, these cells undergo rapid genetic changes that fine-tune the antibody's binding properties, rather like a locksmith adjusting a key to fit a lock more perfectly. This continuous improvement process means that your antibodies literally evolve during an immune response, becoming more and more effective at recognizing and neutralizing their targets. It's Darwinian evolution happening in fast forward within your own body, with the most successful antibody variants being selected and amplified while less effective ones are discarded. The sophistication of this system becomes even more apparent when we consider how antibodies can adapt to face new variants of familiar pathogens. When a virus mutates and changes its surface proteins slightly, your memory B cells can often produce modified antibodies that still recognize the altered invader. It's like having a master key that can be quickly adjusted to open a lock even after someone has changed a few of the tumblers. This adaptability is crucial for dealing with pathogens like influenza viruses, which are notorious for their ability to change their surface proteins from year to year. Your immune system essentially plays an ongoing game of molecular chess with these evolving threats, with antibodies adapting their strategies to counter each new move the virus makes. But perhaps one of the most fascinating aspects of the antibody system is how it can learn to distinguish between closely related threats. Consider how your body can produce different antibodies for different strains of the common cold virus, even though these viruses are quite similar to each other. The molecular differences that antibodies can detect are sometimes smaller than the difference between two nearly identical keys, yet the specificity of recognition is absolute. This exquisite discrimination ability extends beyond just pathogens. Antibodies can distinguish between proteins that differ by just a single amino acid, the molecular building blocks of proteins. It's rather like being able to identify two different people based solely on whether they have a single freckle in slightly different positions. This precision is what makes antibodies such powerful tools not just for natural immunity, but also for medical diagnostics and research. Scientists have learned to harness this precision for creating diagnostic tests that can detect the presence of specific pathogens, toxins, or even cancer markers in blood samples. The same molecular recognition system that protects you from infection can be adapted to serve as an early warning system for various diseases, identifying threats at concentrations so low they would be undetectable by almost any other method. The story of how researchers first learned to produce antibodies outside the body is itself quite remarkable. In the 1972nd, scientists developed a technique for creating what they called monoclonal antibodies, essentially identical antibodies mass-produced from a single B cell. This breakthrough was like learning to photocopy a master key, creating unlimited copies of an antibody with precisely defined properties. The process involves fusing a B cell that produces the desired antibody with an immortal cancer cell, creating a hybrid cell that combines the antibody-producing ability of the B cell with the unlimited growth potential of the cancer cell. These hybrid cells, called hybridomas, can be grown in laboratory conditions indefinitely, churning out identical antibodies for research, diagnostic tests, and medical treatments. Monoclonal antibodies have revolutionized medicine in ways that would have seemed like science fiction just a few decades ago. They're now used to treat cancers, autoimmune diseases, and even to prevent organ rejection in transplant patients. Some of the most effective treatments for conditions like rheumatoid arthritis and certain types of cancer are based on carefully designed antibodies that can seek out and neutralize specific disease-causing molecules with surgical precision. The elegance of using the body's own defense system as a model for medical treatments speaks to the fundamental wisdom embedded in biological systems. Rather than fighting against the body's natural processes, modern medicine increasingly seeks to work with them, enhancing and directing the sophisticated mechanisms that evolution has already perfected. As we drift deeper into this gentle exploration of your microscopic guardians, it's worth pausing to appreciate the sheer scale of the operation happening within you right now. Every second, millions of antibodies are circulating through your bloodstream, each one a molecular sentinel scanning for threats with unwavering vigilance. They flow through vessels so small that red blood cells must squeeze through in single file, yet they navigate this microscopic highway system with remarkable efficiency. The mathematics of the immune system are truly staggering. Your body contains approximately 5 liters of blood, and in each microliter, a volume smaller than a grain of sand, there are typically between 1 and 4 million antibodies floating serenely by. That means you have somewhere between 5 trillion and 20 trillion antibodies patrolling your body at any given moment, each one ready to spring into action should its specific target appear. But these molecular guardians don't work in isolation. They're part of an intricate communication network that spans your entire body, sending and receiving chemical signals that coordinate immune responses with remarkable precision. When antibodies in your throat detect the beginning of a bacterial infection, they can trigger responses that mobilize reinforcements from your bone marrow, activate complement proteins in your blood, and alert immune cells stationed in nearby lymph nodes all within a matter of hours. This communication happens through a language of molecular signals as complex as any human language, but one that's been refined over millions of years of evolutionary pressure. Chemical messages are passed from cell to cell, carrying information about the type of threat detected, its location, and the most appropriate response strategies. It's like having a biological internet running through your body, with antibodies serving as both sensors and messengers in this vast information network. The beauty of this system lies not just in its complexity, but in its restraint. Despite having the power to unleash devastating attacks against invaders, the antibody system normally operates with remarkable precision, avoiding collateral damage to healthy tissues. It's like having a highly trained special forces unit that can eliminate specific targets without disturbing the peaceful neighborhood around them. This precision is maintained through multiple layers of checks and balances. Regulatory T cells patrol the immune system like internal affairs officers, ensuring that antibody responses don't become excessive or misdirected. Anti-inflammatory signals help wind down immune responses once threats have been neutralized, and the natural life cycle of plasma cells ensures that antibody production doesn't continue indefinitely once it's no longer needed. The result is a system that can respond to threats with overwhelming force when necessary, yet return to a state of peaceful vigilance once the danger has passed. It's a level of self-regulation that human-designed systems rarely achieve, maintaining perfect readiness without wasting resources or causing unnecessary disruption to the body's normal functions. As you settle more comfortably into your evening rest, perhaps you can sense, in some subtle way, this vast protective network operating silently within you. The gentle pulse of your heartbeat is circulating these molecular guardians throughout your body, delivering them to every tissue, every organ, every distant outpost of your biological territory. With each breath you take, antibodies in your respiratory tract are sampling the air for potential threats, ready to sound the alarm if anything dangerous attempts to take up residence in your lungs. And in the quiet darkness of your bone marrow, new B cells are being born every moment, each one programmed with a unique molecular signature, adding to your body's vast library of potential responses. It's a process that began before you were born and will continue throughout your life, constantly refreshing and renewing your immune capabilities. The story of antibodies is far from over, and we've only begun to explore their remarkable world. In our continuing journey, we'll discover how these molecular defenders have been turned into life-saving medicines, how they form the basis of vaccination, and how scientists are learning to engineer new antibodies with capabilities that surpass even nature's elegant designs. But for now, as the gentle tide of sleep begins to wash over you, rest in the knowledge that you are watched over by guardians more devoted and capable than any human protector could ever be. They ask nothing of you, require no thanks or recognition, and work tirelessly through every moment of your life to keep you safe from harm. These molecular guardians exist in a state of perpetual readiness, yet their vigilance is neither anxious nor exhausting. Like skilled sentries who have mastered the art of watchful calm, antibodies maintain their protective stance without depleting your body's resources. They drift through your circulatory system with an almost meditative quality, each one carrying its unique molecular signature, like a quietly whispered password that only the right threat will recognize. The journey of an antibody through your body is quite remarkable when you consider the obstacles it must navigate. Your bloodstream is not a simple highway, but rather a complex network of vessels that branch and narrow, like the tributaries of a vast river system. The largest arteries are spacious boulevards where antibodies flow freely alongside red blood cells and plasma proteins. But as the circulation branches into ever smaller vessels, eventually reaching the tiny capillaries that nourish your tissues, the passage becomes more intimate and precise. In these microscopic channels, barely wide enough for a single red blood cell to squeeze through, antibodies must navigate carefully. Yet they do so with remarkable efficiency. Their Y-shaped structure designed to flow smoothly, even through the narrowest passages. It's rather like watching skilled dancers move through a crowded ballroom, never missing a step, never colliding with others, always maintaining their graceful progress toward wherever they're needed most. The relationship between antibodies and the tissues they protect is one of extraordinary intimacy. Consider your skin, that vast protective barrier that serves as your first line of defense against the outside world. Beneath its surface lies a network of tiny blood vessels where antibodies patrol constantly, ready to respond if any pathogen should breach the outer defenses. They don't simply wait passively for threats to appear. Instead, they actively sample the molecular environment, constantly testing and probing for signs of foreign presence. This sampling process is conducted with exquisite sensitivity. Antibodies can detect the presence of threatening molecules at concentrations so low they're measured in parts per trillion. Imagine detecting a single drop of a particular liquid in an Olympic-sized swimming pool. This sensitivity isn't achieved through brute force or aggressive searching, but rather through a kind of molecular listening, a patient attention to the subtle chemical whispers that indicate all is not well. When an antibody does encounter its target, the moment of recognition is both gentle and decisive. There's no violent collision or aggressive attack. Instead, the antibody simply enfolds its target in a molecular embrace that's as specific as it is inescapable. The binding happens through what scientists call van der Waals forces and hydrogen bonds, the same gentle attractions that hold water molecules together or cause morning dew to form on grass. Yet despite their gentleness, these forces create a grip that's remarkably strong and specific. Once bound to their target, antibodies undergo subtle changes in their shape that serve as signals to other parts of the immune system. It's rather like a key turning in a lock, except that in this case, the key changes shape as it turns, creating new surfaces and structures that can be recognized by other molecular partners. These shape changes are so small, they can't be seen even with the most powerful microscopes, yet they're crucial for coordinating the complex responses that follow. The communication that occurs between antibodies and other immune system components happens through a language of molecular shapes and chemical signals that's both ancient and sophisticated. Each type of antibody carries specific molecular signals on its surface, rather like wearing different uniforms that identify their role and capabilities to other immune cells. Some antibodies wear signals that say this target needs to be destroyed immediately, while others carry messages that read this threat requires a more measured response. The immune cells that recognize these signals are equally sophisticated in their responses. Macrophages, those cellular garbage collectors we met earlier, don't simply engulf everything they encounter indiscriminately. Instead, they read the molecular signals on antibody-coated targets and adjust their response accordingly. Some targets are consumed quickly and completely, while others are processed more carefully, with pieces of the destroyed pathogen being preserved and displayed as warnings to other immune cells. This process of antigen presentation is one of the most elegant aspects of the antibody system. When a macrophage consumes an antibody-coated pathogen, it doesn't simply destroy the invader and forget about it. Instead, it carefully preserves small fragments of the pathogen's proteins and displays them on its surface, rather like posting wanted posters in a cellular post office. These displayed fragments can then be recognized by other immune cells, particularly T cells, which help coordinate more sophisticated responses. The T cells that recognize these displayed fragments are like the immune system's intelligence analysts, capable of making complex decisions about what type of response is most appropriate. Some T cells send signals that ramp up antibody production, while others coordinate the activation of killer cells that can eliminate infected tissues. Still, others help regulate the response to ensure it doesn't become excessive or misdirected. This multi-layered coordination creates responses that are far more sophisticated than any individual component could achieve alone. It's rather like a symphony orchestra where each musician is skilled individually, but the real magic happens when they all play together under the guidance of a conductor who can see the larger musical architecture that emerges from their combined efforts. The timing of these coordinated responses is crucial and remarkably precise. In the early stages of an infection, when only a few pathogens have entered your body, the antibody response is measured and focused. But if the threat persists or grows, the response can escalate quickly, with antibody production ramping up exponentially and additional immune cells being recruited to the battle. It's like having a security system that can distinguish between a cat walking across the lawn and an actual intruder, responding appropriately to each situation. This escalation happens through positive feedback loops that amplify successful responses while damping down ineffective ones. When antibodies successfully bind to and neutralize pathogens, the signals they generate encourage the production of more of the same antibodies. Meanwhile, antibodies that fail to find their targets gradually decrease in number, ensuring that your body's resources are focused on the most effective defensive strategies. The memory aspect of the antibody system adds another layer of sophistication to these responses. Those memory B cells we discussed earlier don't just remember that a particular threat existed, they remember exactly how it was defeated. When the same pathogen appears again, sometimes years or even decades later, the memory cells don't start from scratch. Instead, they immediately begin producing the refined, improved antibodies that proved most effective during the previous encounter. This immunological memory is remarkably durable and specific. Studies have found antibodies in elderly individuals that were first produced in response to influenza viruses encountered in childhood, still circulating and ready to provide protection more than half a century later. It's as if your immune system maintains a detailed historical archive, with each entry containing not just information about past threats, but also the most effective strategies for dealing with them should they return. The precision of this memory system is truly extraordinary. Your immune system can distinguish between closely related strains of the same virus, producing slightly different antibodies for each variant. It's like having a librarian who can not only remember every book in a vast collection, but also recall the specific edition, printing, and even the particular copy of each volume. This specificity extends to the molecular level in ways that can seem almost magical. Antibodies can recognize target molecules that differ by just a single atom in the wrong position, or by the presence or absence of a small chemical group attached to a larger protein structure. The lock and key metaphor we used earlier doesn't fully capture this precision. It's more like having a key that can detect not just the shape of a lock, but also its temperature, the metal it's made from, and even whether it's been polished recently. Such exquisite sensitivity allows antibodies to distinguish between your body's own proteins and nearly identical proteins from pathogens. This is crucial for preventing autoimmune reactions, where the immune system mistakenly attacks healthy tissues. The molecular differences that allow this discrimination are sometimes so subtle that they can only be detected by the most sophisticated laboratory instruments, yet antibodies recognize them effortlessly and instantaneously. The production of antibodies with such precise specifications requires a manufacturing process that would be the envy of any human engineer. Each plasma cell, those specialized antibody factories we discussed earlier, contains molecular machinery that can assemble complex proteins with perfect accuracy, time after time. The ribosomes within these cells read genetic instructions like molecular 3D printers, carefully positioning each amino acid in exactly the right location to create a functional antibody. The quality control systems within these cellular factories are equally impressive. Newly made antibodies undergo rigorous testing before they're released into circulation. Proteins that don't fold correctly are identified and recycled, ensuring that only properly functioning antibodies make it out into your bloodstream. It's like having a production line where every product is individually inspected and tested before being approved for use. The speed at which this production can occur is breathtaking. During an active immune response, a single plasma cell can produce and secrete up to 2,000 antibodies every second. To put this in perspective, if you could work at the same relative pace, you could assemble a complex piece of furniture every few seconds, working continuously for days without rest. Yet despite this incredible productivity, the process operates with minimal waste and remarkable energy efficiency. Plasma cells have evolved to focus almost entirely on antibody production, stripping away unnecessary cellular components and dedicating virtually all their resources to this single crucial task. It's a level of specialization that allows them to achieve production rates that seem almost impossible. The antibodies that emerge from this manufacturing process aren't just molecular tools, they're architectural marvels in their own right. Each one contains hundreds of amino acids, arranged in precisely the correct sequence, and folded into a three-dimensional structure that's both stable and functional. The folding process itself is a minor miracle, with long chains of amino acids spontaneously twisting and turning into their correct shapes through interactions that are still not fully understood by scientists. The stability of these folded structures is crucial for antibody function. Your antibodies must maintain their precise shapes while traveling through environments that range from the relatively gentle conditions inside your blood vessels to the harsh, acidic environment of your stomach. They must remain functional at your normal body temperature, yet also withstand the elevated temperatures that occur during fever. It's like designing a delicate instrument that can function perfectly whether it's in a climate-controlled laboratory or a desert sandstorm. The durability of antibodies is matched by their longevity. Some antibodies can remain active in your bloodstream for weeks or even months, providing continuous protection against their specific targets. This persistence is achieved through careful molecular engineering that protects the antibodies from degradation by enzymes and other destructive forces in your body. It's as if each antibody is equipped with its own molecular preservation system, keeping it functional for as long as it might be needed. As you rest there in the gathering quiet of evening, perhaps you can imagine these remarkable molecules continuing their endless patrol through your body. They move with the steady rhythm of your heartbeat, circulating through arteries and veins, seeping through tissue spaces, and standing ready at every potential point of entry where threats might appear. In your respiratory system, specialized antibodies called secretory IgA are embedded in the mucus that lines your airways, creating a protective barrier that screens every breath you take. In your digestive system, other antibodies patrol the lining of your intestines, ready to neutralize any harmful bacteria or toxins that might have contaminated your food. Even in the tear film that protects your eyes and the saliva that keeps your mouth healthy, antibodies stand guard with patient vigilance. The coordination between all these different antibody populations is maintained through chemical signals that flow through your lymphatic system, a parallel circulatory network that serves as the immune system's private communication channel. Through this network, antibodies and immune cells can share information about threats and coordinate responses across vast distances within your body. This biological internet operates continuously, processing information, updating threat assessments, and adjusting defensive strategies in real time. It's a level of coordination that makes even the most sophisticated computer networks seem primitive by comparison, yet it operates without any central command structure or conscious oversight. Each component simply follows its programmed responses, yet somehow the combined result is a coherent, intelligent defense system that adapts and learns from every encounter. The elegance of this system becomes even more apparent when you consider how it balances competing demands. Your antibodies must be ready to respond aggressively to genuine threats, yet they must also avoid overreacting to harmless substances in your environment. They must maintain constant vigilance without wasting energy on false alarms. They must be specific enough to distinguish between closely related molecules, yet flexible enough to adapt to new variants of familiar threats. This balance is achieved through mechanisms that are still being discovered by immunologists. Recent research has revealed that antibodies don't just bind to their targets, they can also influence each other's behavior through subtle molecular interactions. Some antibodies can enhance the effectiveness of others, while different antibodies can moderate responses to prevent them from becoming excessive. The picture that emerges from this research is of an immune system that's even more sophisticated and self-regulating than previously imagined. It's not just a collection of molecular weapons, but rather a complex adaptive system that learns, remembers, and continuously refines its strategies for protecting the body it serves. As we prepare to explore even deeper into this microscopic realm, we'll discover how scientists have learned to work with these natural systems, creating vaccines that train your antibodies to recognize new threats, and developing therapeutic antibodies that can treat diseases once thought incurable. We'll see how the fundamental principles that govern your body's natural defenses are being applied to create new medical technologies that could transform healthcare in the years to come. But for now, as the night deepens around you and sleep begins to call more insistently, rest assured that you are protected by defenders whose sophistication and dedication surpass anything human ingenuity has yet devised. They ask nothing of you but the simple act of living, and in return, they offer you the gift of health, the blessing of protection, and the quiet assurance that you are never truly alone in this vast and sometimes challenging world. The remarkable thing about your antibodies is that they don't work in isolation. They're part of an intricate network that extends far beyond your bloodstream into every corner of your biological existence. Right now, as you listen to these words, specialized antibodies are stationed at the very boundaries where your body meets the outside world, standing guard at the delicate interfaces where life and environment intersect. Consider your skin, that vast protective organ that wraps around you like a living coat of armor. Beneath its surface lies a complex network of immune surveillance, where antibodies patrol the tiny spaces between cells, sampling the molecular environment for signs of unwanted visitors. These antibodies don't simply float passively through your tissues, they actively explore, probing and testing with the patience of experienced sentinels who understand that vigilance is the price of safety. The antibodies in your skin are particularly fascinating because they must distinguish between the countless harmless microorganisms that naturally live on your body's surface and the occasional pathogen that might pose a genuine threat. Your skin hosts an entire ecosystem of bacteria, fungi, and other microscopic creatures that have evolved alongside humanity for millions of years. These resident microbes aren't invaders. They're more like peaceful neighbors who help maintain the health of your skin by competing with harmful organisms for resources and space. Your antibodies have learned to recognize these friendly residents and leave them undisturbed while remaining alert for truly dangerous intruders. It's rather like having security guards who can distinguish between the regular mail carrier and a suspicious stranger, responding appropriately to each without creating unnecessary alarm or disruption. This discrimination becomes even more remarkable when you consider the molecular scale at which these decisions are made. The difference between a helpful bacterium and a harmful one might be as subtle as a single protein on their surface, yet your antibodies can make this distinction with absolute precision. They've been trained by millions of years of evolutionary refinement to recognize the molecular signatures that truly matter, filtering out the noise to focus on genuine threats. The training process for this recognition begins even before you're born. During fetal development, your immune system starts learning to distinguish between self and non-self, between what belongs in your body and what doesn't. This education continues throughout your life, with each new encounter adding to your immune system's vast database of molecular patterns and appropriate responses. But perhaps most remarkably, your antibodies can adapt their responses based on context. The same antibody that might trigger a gentle, measured response to a minor bacterial intrusion in healthy tissue might coordinate a much more aggressive response if that same bacterium appears in a wound or damaged area where it could cause serious harm. It's like having guards who can assess not just who is trying to enter, but also whether the timing and location of that entry are appropriate. This contextual awareness extends throughout your body's various organ systems, each with its own specialized population of antibodies adapted to local conditions. In your respiratory system, for instance, the antibodies that protect your lungs must deal with the constant influx of airborne particles, pollutants, and microorganisms that enter with every breath you take. These respiratory antibodies are embedded in the mucus that lines your airways, creating a sticky trap that captures potential threats before they can reach the delicate gas exchange surfaces deep in your lungs. The mucus itself is a marvel of biological engineering, a complex gel that's mostly water but contains proteins, sugars, and other molecules that create a protective barrier with remarkable properties. The antibodies within this mucus don't just float randomly. They're strategically positioned and oriented to maximize their ability to intercept and neutralize airborne threats. It's like having a three-dimensional net where each strand is precisely placed to catch specific types of molecular fish. When you breathe in through your nose, the air passes through a series of increasingly fine filters, each one designed to remove different categories of potential threats. Larger particles get caught by the coarse hairs in your nostrils, medium-sized particles are trapped by the mucus in your nasal passages, and the smallest particles, including many viruses and bacteria, encounter the antibody-laden mucus deeper in your respiratory system. The antibodies in your respiratory tract are particularly sophisticated because they must distinguish between harmless environmental particles and genuine biological threats. Every breath you take contains pollen, dust, fragments of dead skin cells, and countless other particles that pose no danger to your health. Your respiratory antibodies have learned to ignore these harmless intruders while remaining vigilant for the molecular signatures of actual pathogens. This selective attention is achieved through a process that's both elegant and efficient. Rather than responding to every foreign particle, your respiratory antibodies focus on specific molecular patterns that are characteristic of dangerous microorganisms. They look for proteins that are common to bacterial cell walls, genetic material from viruses, or toxins produced by harmful fungi. It's like having a security system that can distinguish between a delivery truck and a suspicious vehicle based on subtle but reliable identifying features. The coordination between different parts of your respiratory immune system is equally impressive. When antibodies in your upper respiratory tract detect the beginning of a viral infection, they can send chemical signals that activate immune responses throughout your entire respiratory system. Antibodies in your sinuses, throat, trachea, and lungs all receive these molecular messages and begin preparing for the possibility that the infection might spread to their areas. This advanced warning system allows your body to mount a coordinated defense before an infection can establish itself. It's rather like having an early warning radar network that can detect incoming threats and alert all defensive positions simultaneously. The speed of this communication is remarkable. Chemical signals can travel from your nose to your lungs in a matter of minutes, allowing your entire respiratory system to shift from routine surveillance to active defense almost instantaneously. Your digestive system presents an even more complex challenge for your antibodies. Every day, you consume foods that contain millions of foreign proteins, along with bacteria, yeasts, and other microorganisms that naturally occur in even the most carefully prepared meals. Your digestive antibodies must somehow distinguish between these harmless food components and genuine threats, while allowing normal digestion to proceed without interference. The antibodies that line your intestines are masters of this discrimination. They've learned to recognize the molecular signatures of dangerous bacteria like Salmonella or E. coli, while ignoring the beneficial bacteria that help you digest food and synthesize vitamins. They can identify bacterial toxins at incredibly low concentrations while remaining indifferent to the complex mixture of proteins, carbohydrates, and other molecules that make up your daily meals. This selective tolerance is crucial for maintaining your health. If your digestive antibodies were too aggressive, they might interfere with normal digestion or attack the beneficial bacteria that are essential for your intestinal health. If they were too passive, dangerous pathogens could establish infections that might threaten your life. The balance they maintain is both delicate and crucial, requiring constant adjustment based on the changing conditions within your digestive tract. The environment within your intestines is particularly challenging for antibodies because it's constantly changing as food moves through your system. The acidity, temperature, and chemical composition of your intestinal contents vary dramatically from moment to moment. Yet, your antibodies must remain functional and effective throughout these fluctuations. They've evolved special structural features that protect them from degradation by digestive enzymes, while maintaining their ability to recognize and bind to threats. One of the most fascinating aspects of your digestive immune system is how it learns to tolerate new foods while remaining vigilant for genuine threats. When you eat something for the first time, Your intestinal antibodies carefully sample the new proteins and other molecules, gradually learning to recognize them as harmless food components rather than foreign invaders. This learning process is usually so smooth and efficient that you're completely unaware it's happening. However, sometimes this tolerance system breaks down, leading to food allergies or intolerances. In these cases, antibodies mistakenly identify harmless food proteins as threats, triggering inflammatory responses that can range from mild discomfort to life-threatening reactions. It's like having a security system that's been programmed to treat the mail carrier as a dangerous intruder, creating chaos and disruption where there should be peaceful coexistence. The antibodies in your bloodstream face their own unique challenges. Unlike the antibodies stationed at your body's surfaces, which deal primarily with threats trying to enter your system, blood-borne antibodies must patrol an internal environment that's normally sterile, but can become contaminated if your surface defenses are breached. They serve as your last line of defense, the final barrier between invading pathogens and the vital organs that keep you alive. Blood-borne antibodies must be prepared to deal with a wide variety of threats that might enter your circulation through wounds, insect bites, medical procedures, or by overwhelming your surface defenses. They need to be able to recognize and neutralize bacteria, viruses, fungi, parasites, and toxins, essentially any harmful substance that might find its way into your bloodstream. The speed of response required from blood-borne antibodies is particularly demanding because threats in your circulation can spread throughout your body within minutes. A bacterium that enters through a small cut on your finger could theoretically reach your brain, heart, or kidneys in less time than it takes to read this sentence. Your blood-borne antibodies must be ready to respond immediately, without the luxury of time for recognition and preparation. This immediacy is achieved through the constant presence of preformed antibodies that circulate continuously through your vascular system. Unlike the antibodies at your body's surfaces, which can be produced locally in response to specific threats, your blood-borne antibodies must be manufactured in advance and maintained at ready-to-use concentrations. It's like having a rapid response team that's always equipped and positioned for immediate deployment. The logistics of maintaining this circulating antibody force are quite remarkable. Your bone marrow and other antibody-producing tissues must continuously manufacture and release fresh antibodies to replace those that are consumed in defensive actions or that simply age out of usefulness. The production must be carefully balanced. Too few antibodies would leave you vulnerable to infection, while too many would waste precious biological resources and might even interfere with normal physiological processes. The antibodies that patrol your lymphatic system occupy a unique position in your body's defensive network. The lymphatic system serves as both a drainage network, collecting excess fluid from your tissues, and a highway for immune cells traveling between different parts of your body. Antibodies in your lymphatic fluid can sample molecules from throughout your body, providing a kind of real-time surveillance report on your overall health status. Lymphatic antibodies are particularly important for detecting threats that might not be immediately obvious at other sites. Sometimes pathogens can establish small, localized infections that don't initially trigger strong responses from surface or blood-borne antibodies. These hidden infections might slowly spread through your tissues, causing damage before other parts of your immune system become aware of the threat. The antibodies in your lymphatic system serve as an early warning network for these subtle threats. As lymphatic fluid drains from your tissues, it carries with it molecular evidence of any infections or other problems that might be developing. Lymphatic antibodies can detect this evidence and trigger responses that bring additional immune resources to bear on emerging threats before they become serious problems. The movement of antibodies through your lymphatic system also facilitates communication between different parts of your immune network. Antibodies produced in response to a threat in one part of your body can travel through lymphatic channels to other areas, carrying information about the nature of the threat and the most effective responses. It's like having a biological internet that allows different parts of your immune system to share intelligence and coordinate their activities. Your lymph nodes serve as processing centers within this network, filtering lymphatic fluid and concentrating immune responses where they're most needed. When antibodies in your lymphatic system detect a threat, they can trigger the activation of lymph nodes in the affected area. These activated nodes become centers of intense immune activity, producing additional antibodies and coordinating responses from other types of immune cells. The swelling of lymph nodes that you might notice during an infection is actually a sign that this system is working properly. The nodes enlarge because they're filling with immune cells and antibodies mobilized to fight the detected threat. It's a visible indication of the intense microscopic activity taking place within your immune system, millions of cells working together to identify, isolate, and eliminate whatever pathogen has triggered the response. Even your nervous system has its own specialized antibody defenses, though these operate under particularly challenging constraints. Your brain and spinal cord are protected by the blood-brain barrier, a selective filter that prevents most substances in your blood from entering your nervous tissue. This barrier is essential for protecting your delicate neural networks from toxins and other harmful substances, but it also makes it difficult for antibodies to reach sites of infection within your nervous system. The antibodies that do manage to cross the blood-brain barrier must be highly specialized and carefully regulated. They need to be able to recognize and neutralize genuine threats to your nervous system, while avoiding interference with the complex chemical processes that underlie thought, memory, and consciousness. It's perhaps the most delicate balancing act required of any antibodies in your body. When infections do manage to penetrate your nervous system, the antibody response must be swift and decisive, yet also precisely controlled to avoid causing damage to irreplaceable neural tissue. The stakes are particularly high because neurons, unlike most other cells in your body, cannot be easily replaced if they're damaged during an immune response. The coordination required for nervous system immune responses involves communication between antibodies, specialized immune cells, and the cells that maintain the blood-brain barrier itself. This communication must be rapid and accurate, allowing for quick responses to genuine threats while maintaining the protective isolation that keeps your brain safe from the normal turbulence of your body's immune activities. As you rest there tonight, perhaps growing drowsier with each passing moment, all of these different antibody populations continue their quiet work throughout your body. They move with the rhythm of your breathing, the steady pulse of your heartbeat, the gentle flow of lymphatic fluid through your tissues. They stand watch at every boundary, patrol every pathway, and maintain their vigilant surveillance of every space where threats might appear. The remarkable thing about this vast defensive network is how seamlessly it operates, without any conscious direction from you. You don't need to remember to activate your respiratory antibodies when you breathe, or consciously deploy your digestive antibodies when you eat. The system manages itself with a sophistication that would be impossible to achieve through conscious control, responding to thousands of potential threats every day, while allowing the normal activities of life to proceed without interruption. This autonomous operation extends to the continuous maintenance and renewal of your antibody forces. Old antibodies are constantly being recycled and replaced with fresh ones. Production levels are automatically adjusted based on current threat levels, and the overall composition of your antibody population gradually evolves to match the challenges present in your environment. It's like having a self-managing security service that continuously upgrades its equipment and training without ever needing external oversight or instruction. The longevity of your antibody memory system means that protection established decades ago continues to serve you today, while new exposures add to your defensive capabilities for potential use years or decades in the future. Your current immune status reflects not just recent threats, but the accumulated experience of your entire lifetime, every infection you've survived, every vaccination you've received, every exposure that has helped train your immune system to recognize and respond to danger. This biological memory is remarkably durable and specific, maintaining detailed information about threats you may have encountered only once, years ago. Yet, it's also dynamic and adaptive, capable of updating and refining its responses as new variants of familiar threats appear. It's a library that never forgets, yet never stops learning. As we continue deeper into this exploration of your body's remarkable defenders, we'll discover how modern medicine has learned to work with these natural systems, creating vaccines that safely train your antibodies to recognize new threats, and developing therapeutic antibodies that can treat diseases your natural immune system might struggle to handle alone. We'll explore how scientists have unlocked the secrets of antibody production and learned to create designer antibodies with capabilities that enhance and complement your body's own protective mechanisms. But for now, in the gentle quietude of this moment, rest in the knowledge that you are protected by a system of extraordinary sophistication and unwavering dedication. These molecular guardians ask nothing of you but the privilege of serving, and in return they offer you the precious gift of health, not just for tonight, but for all the nights and days to come. The story of how science first learned to harness the power of antibodies is filled with moments of serendipity, brilliant insight, and the kind of patient observation that transforms our understanding of life itself. It began, as many great discoveries do, with someone noticing something that seemed almost too simple to be important, yet proved to hold the key to saving millions of lives. In the late 1702, an English country doctor named Edward Jenner observed something curious about the milkmaids in his rural practice. These young women, who spent their days tending to dairy cows, seemed remarkably resistant to smallpox, a disease that was then one of humanity's most feared killers. Smallpox claimed the lives of nearly a third of those it infected, leaving survivors scarred and sometimes blind. Yet the milkmaids, who regularly contracted the much milder cowpox from their bovine charges, appeared to be naturally protected. Jenner's insight was both simple and revolutionary. Perhaps the mild cowpox infection was somehow training the body to recognize and fight off the more dangerous smallpox virus. In 1796, he tested this theory in what would today be considered an ethically questionable experiment, deliberately infecting a young boy with cowpox and then, weeks later, exposing him to smallpox. The boy remained healthy, and the age of vaccination was born. What Jenner didn't know, couldn't have known with the scientific tools available at the time, was that he had discovered a way to deliberately trigger antibody production. The cowpox virus was similar enough to smallpox that antibodies trained to recognize one could effectively neutralize the other, yet different enough that the cowpox infection posed little danger. He had, in essence, created the world's first molecular training program, teaching the immune system to recognize a threat it had never encountered. This principle of vaccination, from the Latin word for cow, vacca, would eventually become one of medicine's most powerful tools. But it would be more than a century before scientists understood the microscopic mechanisms that made Jenner's cowpox inoculations so effective. The antibodies responsible for this protection remained invisible and mysterious, their existence inferred only from the immunity they provided. The gradual unveiling of the antibody system reads like a detective story, with each generation of scientists adding crucial clues to an increasingly complex picture. In the 1882nd, Louis Pasteur expanded on Jenner's work, developing vaccines for rabies and anthrax using weakened or killed versions of the disease-causing microorganisms. Pasteur understood that these vaccines were training the body's defenses, though the precise nature of those defenses remained elusive. It was Emil von Behring, working in Robert Koch's laboratory in Berlin, who first proved that immunity could be transferred from one animal to another through blood serum. His experiments with diphtheria and tetanus showed that something in the blood of immune animals, something he called antitoxins, could protect healthy animals from these deadly diseases. For this discovery, Behring became the first recipient of the Nobel Prize in Physiology or Medicine in 1901. The antitoxins that Behring discovered were, of course, antibodies, though their true nature wouldn't be understood for decades. Scientists could see their effects: protection against disease, neutralization of toxins, but the antibodies themselves remained as mysterious as ghosts, detectable only by their actions. It was rather like studying an invisible artist by examining their paintings, trying to understand the creator through their creations. The development of better microscopy and biochemical techniques in the early 1900s gradually began to reveal the physical reality behind these protective effects. Scientists learned that antibodies were proteins, complex molecules that could be separated from blood and studied in isolation. They discovered that different antibodies had different properties. Some worked better against bacteria, others against viruses, and still others against toxic substances. By the 1942nd, researchers had developed techniques for producing antibodies on a large scale, using horses, rabbits, and other animals as living antibody factories. These animals would be immunized with specific pathogens or toxins, and their blood serum would be harvested to create therapeutic preparations rich in protective antibodies. It was a crude but effective approach that saved countless lives during an era when bacterial infections were still major killers. The discovery of antibiotics in the mid-20th century overshadowed antibody therapy for several decades, as these powerful drugs proved more convenient and often more effective than biological treatments. But scientists never lost interest in understanding and harnessing the exquisite specificity of antibodies. They recognized that while antibiotics worked like molecular sledgehammers, effective but sometimes destructive, antibodies operated more like molecular keys, capable of targeting specific threats with surgical precision. The breakthrough that would revolutionize antibody science came in 1975, when Georges Kohler and Cesar Milstein developed a technique for producing monoclonal antibodies. Their method involved fusing antibody-producing B cells with immortal cancer cells, creating hybrid cells that could produce unlimited quantities of identical antibodies. It was like discovering how to make unlimited copies of a master key, each one guaranteed to fit its specific molecular lock perfectly. This technique opened up possibilities that had previously existed only in the realm of science fiction. For the first time, scientists could produce pure, consistent preparations of antibodies with precisely defined properties. They could create antibodies that recognized specific cancer cells, viral proteins, bacterial toxins, or any other molecular target they chose to study. The era of designer antibodies had begun. The applications of monoclonal antibodies expanded rapidly through the 1982nd and 1992nd. They became essential tools for medical diagnostics, allowing doctors to detect diseases with unprecedented accuracy and sensitivity. Pregnancy tests, Hawaii V tests, and countless other diagnostic procedures relied on antibodies' ability to recognize specific molecular signatures with perfect reliability. More dramatically, monoclonal antibodies began to emerge as powerful therapeutic agents. The first therapeutic antibody was approved for medical use in 1986, a treatment designed to prevent organ rejection in kidney transplant patients. This antibody worked by selectively targeting and neutralizing the immune cells that would otherwise attack the transplanted organ, allowing the recipient's body to accept the new kidney without compromising their overall immune function. The success of this first therapeutic antibody opened the floodgates for a new era of antibody-based medicine. Scientists began developing antibodies to treat cancer, autoimmune diseases, inflammatory conditions, and infectious diseases. Each new antibody was like a smart missile, capable of seeking out its specific target while leaving healthy tissues unharmed. Cancer treatment was particularly transformed by therapeutic antibodies. Traditional cancer treatments, chemotherapy and radiation, worked by attacking all rapidly dividing cells, which included both cancer cells and many healthy cells. The side effects could be devastating, and the treatments often seemed almost as dangerous as the diseases they were meant to cure. Antibody-based cancer treatments offered a more elegant approach. Scientists learned to identify proteins that were present on cancer cells but absent from healthy cells, then develop antibodies that could recognize these cancer-specific targets. Some of these therapeutic antibodies worked by directly attacking cancer cells, while others delivered toxic substances specifically to tumors, sparing healthy tissues from damage. The development of therapeutic antibodies for autoimmune diseases represented another triumph of molecular precision. In conditions like rheumatoid arthritis, multiple sclerosis, and inflammatory bowel disease, the immune system mistakenly attacks the body's own tissues. Traditional treatments involved suppressing the entire immune system, leaving patients vulnerable to infections and other complications. Therapeutic antibodies offered a more targeted approach. Instead of shutting down the entire immune system, these treatments could neutralize specific inflammatory molecules or block particular immune pathways that were driving the autoimmune process. Patients could maintain most of their immune function while getting relief from the destructive autoimmune reactions that were causing their symptoms. The precision of these targeted treatments was remarkable. Scientists could develop antibodies that blocked specific inflammatory signals while leaving other beneficial immune functions intact. It was like being able to silence one instrument in an orchestra without affecting the others, maintaining the overall harmony while eliminating discordant notes. As therapeutic antibodies became more sophisticated, scientists learned to enhance their natural properties through genetic engineering. They could modify antibodies to make them last longer in the bloodstream, penetrate tissues more effectively, or trigger more powerful immune responses. Some engineered antibodies were designed to carry radioactive substances or toxic drugs directly to cancer cells, turning the antibodies into guided missiles with devastating warheads. The development of humanized antibodies represented another major advance. Early therapeutic antibodies were often produced in mice or other animals, which meant that human patients' immune systems sometimes recognized them as foreign and mounted immune responses against them. This could reduce the effectiveness of the treatment and cause dangerous allergic reactions. Scientists solved this problem by learning to replace most of the animal-derived portions of therapeutic antibodies with human equivalents, leaving only the small regions responsible for target recognition unchanged. These humanized antibodies were much less likely to trigger unwanted immune reactions while retaining their therapeutic effectiveness. The creation of fully human antibodies took this approach even further. Using sophisticated genetic techniques, scientists could create antibodies that were indistinguishable from those naturally produced by the human immune system. These antibodies combine the precision of monoclonal antibodies with the safety and compatibility of human-derived proteins. The range of conditions treatable with antibody-based therapies continued to expand throughout the 2002 and 2010. Antibodies were developed to treat everything from age-related macular degeneration to severe asthma, from migraine headaches to rare genetic disorders. Each new application demonstrated the versatility of antibodies as therapeutic agents. Some of the most dramatic successes came in the treatment of previously incurable cancers. Antibodies targeting specific proteins on blood cancer cells proved remarkably effective, transforming conditions that had been virtual death sentences into manageable chronic diseases. Patients who would have died within months of diagnosis were living for years or even decades with good quality of life. The COVID-19 pandemic showcased both the power and the speed of modern antibody development. Within months of identifying the virus responsible for the pandemic, scientists had developed monoclonal antibodies that could neutralize it. These treatments provided hope for high-risk patients and helped bridge the gap while vaccines were being developed and distributed. The pandemic also demonstrated how quickly antibody-based treatments could be adapted to address new challenges. As new variants of the virus emerged, Scientists could test existing therapeutic antibodies against them and develop updated versions when needed. It was a real-time demonstration of the flexibility and responsiveness of antibody-based medicine. Beyond their therapeutic applications, antibodies have become indispensable tools for scientific research. They allow researchers to study specific proteins within living cells, track the progression of diseases, and understand the molecular mechanisms underlying health and illness. Many of the fundamental discoveries about how your immune system works were made possible by antibodies designed to recognize and mark specific immune system components. The use of fluorescently labeled antibodies has created stunning visual representations of cellular processes. Scientists can now watch antibodies seeking out their targets within living tissues, see how immune cells communicate with each other, and observe the real-time dynamics of immune responses. These visualizations have transformed our understanding of immunology from abstract concepts to visible, dynamic processes. The precision of antibodies has also made them valuable for studying brain function and neurological diseases. Scientists have developed antibodies that can cross the blood-brain barrier and recognize specific proteins associated with conditions like Alzheimer's disease, Parkinson's disease, and multiple sclerosis. These tools are providing new insights into how these devastating conditions develop and progress. Some of the most exciting recent developments involve using antibodies to deliver other therapeutic agents to specific locations within the body. Scientists have learned to attach drugs, genes, radioactive isotopes, and other therapeutic substances to antibodies, creating combination treatments that can target diseased tissues with remarkable precision. It's like having a molecular postal service that can deliver packages to specific addresses within your body. The field of antibody-drug conjugates represents a particularly promising approach to cancer treatment. These molecules combine the targeting ability of antibodies with the cell-killing power of potent drugs. The antibody portion seeks out cancer cells, while the drug portion destroys them once the target is reached. This approach allows doctors to use drugs that would be far too toxic if given systemically, since the antibodies ensure that most of the drug reaches only the intended target. Recent advances in genetic engineering have enabled the creation of entirely new types of antibody-based treatments. Scientists can now design antibodies that change their properties in response to specific environmental conditions, antibodies that can simultaneously target multiple different molecules, and even artificial antibodies with capabilities that don't exist in nature. Some researchers are developing antibodies that can be controlled externally, turning their activity on or off in response to light, magnetic fields, or specific chemical signals. These controllable antibodies could provide unprecedented precision in medical treatments, allowing doctors to activate therapies only when and where they're needed. The concept of antibody cocktails, combinations of different antibodies that work together to achieve better results than any single antibody could provide alone, has proven particularly effective for treating complex diseases. Just as your natural immune system uses multiple types of antibodies simultaneously, these therapeutic combinations can address different aspects of a disease or overcome the resistance that sometimes develops to single antibody treatments. Looking toward the future, scientists are exploring ways to enhance the natural antibody systems within patients' own bodies. Rather than providing therapeutic antibodies from external sources, these approaches aim to stimulate or redirect the patient's immune system to produce more effective antibodies against disease targets. Gene therapy approaches are being developed to provide patient cells with the genetic instructions needed to produce therapeutic antibodies internally. This could provide long-lasting treatments that wouldn't require repeated injections or hospital visits. It's like teaching your body to produce its own customized medicine. The development of artificial immune systems represents perhaps the most ambitious extension of antibody science. Researchers are working to create synthetic biological circuits that could supplement or enhance natural immune functions, providing protection against threats that the natural immune system struggles to handle effectively. These synthetic immune systems might include engineered antibodies with enhanced capabilities, artificial immune cells programmed to perform specific functions, or even completely artificial immune networks that could operate independently of natural immune processes. While still largely experimental, these approaches point toward a future where the boundary between natural and artificial immunity becomes increasingly blurred. The integration of artificial intelligence and machine learning into antibody development is accelerating the pace of discovery and reducing the time needed to develop new treatments. AI systems can predict which antibody designs are most likely to be effective against specific targets, identify potential side effects before clinical testing begins, and optimize treatment protocols for individual patients. These computational approaches are making it possible to develop personalized antibody treatments tailored to each patient's specific disease characteristics and immune system profile. Rather than using one-size-fits-all treatments, doctors may soon be able to prescribe antibody therapies that are optimized for each individual patient's unique biological circumstances. The convergence of antibody science with other advanced technologies is opening up possibilities that would have seemed like pure fantasy just a few decades ago. Nanotechnology is being used to create microscopic delivery systems that can carry antibodies to specific locations within the body. Robotics and automation are making it possible to produce complex antibody treatments more quickly and affordably than ever before. As you rest there tonight, perhaps beginning to feel the gentle pull of sleep, it's worth marveling at how far we've travelled from Edward Jenner's simple observation about milkmaids and cowpox. That single insight about the body's ability to learn and remember has blossomed into an entire medical revolution, transforming antibodies from mysterious protective substances into precisely engineered therapeutic tools. The antibodies working silently within your body right now represent the culmination of billions of years of evolutionary refinement, enhanced by decades of scientific innovation and engineering. They embody both the ancient wisdom of biological systems and the cutting-edge insights of modern medicine, working together to provide you with protection that surpasses anything available to previous generations. Yet for all our scientific advances, the fundamental elegance of the antibody system remains unchanged. These molecular guardians continue to patrol your body with the same patient vigilance that has protected life for millions of years, asking nothing in return for their service except the privilege of keeping you healthy and safe. The future promises even more remarkable developments in antibody science and medicine, treatments that can cure cancers, prevent autoimmune diseases, and protect against infectious diseases that haven't even been discovered yet. Diagnostic tests that can detect illness before symptoms appear, and preventive treatments that can stop diseases from developing in the first place. But perhaps the most profound lesson from the story of antibody science is how much we can accomplish by working with, rather than against, the natural systems that sustain life. The most successful medical treatments have always been those that enhance and support the body's own healing mechanisms, and antibodies represent the ultimate expression of this collaborative approach. As the night deepens around you and your thoughts begin to drift towards sleep, take comfort in knowing that this remarkable partnership between natural wisdom and human ingenuity continues to evolve and improve. The antibodies that protect you tonight are the beneficiaries of both ancient evolutionary processes and the most advanced scientific knowledge, working together in perfect harmony to ensure your continued health and well-being. The gentle rhythm of your breathing carries these molecular defenders throughout your body, delivering them to every tissue and organ where they might be needed. With each heartbeat, millions of antibodies flow through your circulatory system, maintaining their vigilant watch over your biological kingdom. They move with the quiet confidence of experienced guardians, alert but untroubled, ready for whatever challenges might arise while you rest. And in laboratories and research centers around the world, scientists continue their patient work of understanding and improving these remarkable systems, always seeking new ways to enhance the natural protections that keep us all healthy and whole. The story of antibodies is far from over, and the next chapters promise to be even more extraordinary than those we've already witnessed. In this final gentle chapter of our journey through the microscopic realm of your body's defenders, let's take a moment to step back and marvel at the extraordinary symphony of protection that surrounds you at every moment. As you lie there in the gathering quietude of evening, perhaps feeling the soft tug of sleep beginning to claim your thoughts, you are witnessing, though you cannot see or feel it, one of the most sophisticated biological performances ever devised by nature. The antibodies we've explored tonight exist in a state of perpetual readiness that would exhaust any human sentinel, yet they maintain their vigilance with an effortless grace that speaks to millions of years of evolutionary refinement. They move through your body like silent dancers, each one perfectly choreographed to its specific role in the vast ballet of immune protection. There's something deeply poetic about the way these molecular guardians go about their work, methodical yet responsive, powerful yet gentle, ancient in their wisdom yet constantly adapting to meet new challenges. Consider the remarkable fact that right now, as your eyelids grow heavier and your breathing slows, trillions of these tiny defenders are actively patrolling every corner of your biological territory. They flow through blood vessels so narrow that they must travel in single file, yet they do so with the confidence of travelers who know every street and alleyway in their domain. They pause at checkpoints throughout your tissues, sampling the molecular environment with the patience of expert wine tasters, distinguishing between the familiar and the foreign with exquisite precision. The communication network that connects all these antibody populations is perhaps even more remarkable than the antibodies themselves. Chemical messages flow constantly through your lymphatic system, carrying news of threats detected, reinforcements needed, and victories achieved. It's a biological internet that operates at the speed of chemistry, processing vast amounts of information and coordinating responses across distances that, on the cellular scale, are equivalent to continents. This communication system allows your body to mount coordinated responses that would impress any military strategist. When antibodies in your respiratory tract detect the early signs of a viral infection, they don't simply respond locally, they send out molecular distress signals that can mobilize immune resources from throughout your body. Within hours, antibody production can be ramped up in distant organs, creating a coordinated defense that the virus never sees coming. The elegance of this system lies not just in its complexity, but in its restraint. Despite having the power to unleash devastating attacks against perceived threats, your antibody system operates with remarkable discrimination. It distinguishes between genuine dangers and harmless substances with a precision that would be impossible to achieve through conscious effort. Every breath you take contains thousands of foreign particles, yet your antibodies respond only to those that pose actual threats, allowing you to live in a world full of potential allergens and irritants without constant immune turmoil. This discrimination is achieved through layers of recognition systems that operate like nested security clearances. Primary recognition identifies whether a substance is foreign to your body. Secondary systems determine whether that foreign substance poses an actual threat. Tertiary mechanisms decide what level of response is appropriate, ensuring that the cure never becomes worse than the disease. And throughout it all, regulatory systems monitor the response to ensure it doesn't become excessive or misdirected. The memory aspect of your antibody system adds yet another dimension to this remarkable story. Those memory B cells we discussed earlier don't just remember past encounters, they remember them with a detail and accuracy that would shame the most sophisticated computer database. They can distinguish between closely related variants of the same pathogen, maintaining specific responses for each one while remaining ready to adapt if new variants appear. This biological memory is what allows vaccines to work so effectively. When you receive a vaccination, You're essentially providing your antibody system with a safe preview of a potential threat, allowing it to develop and refine its defenses without the risk of actual disease. It's like conducting a fire drill that prepares everyone for the real emergency without exposing them to actual danger. The duration of this immunological memory is truly extraordinary. Studies have found antibodies in elderly individuals that were first produced in response to infections encountered in childhood, still circulating and functional after 8 or 9 decades. It's as if your immune system maintains a lifelong diary, with each entry representing not just a record of past encounters, but a standing army ready to respond should the same threat ever return. Modern medicine's ability to work with these natural systems represents one of humanity's greatest intellectual achievements. Rather than trying to replace or override your body's own defenses, the most successful medical treatments enhance and direct them, creating partnerships between natural wisdom and human ingenuity that benefit both. The therapeutic antibodies developed by scientists don't fight against your natural immune system, they work alongside it, providing additional capabilities while respecting the elegant balance that keeps you healthy. The development of these medical applications required scientists to become, in essence, molecular engineers, learning to modify and improve upon designs that nature had spent millions of years perfecting. Yet the most successful therapeutic antibodies are those that most closely mimic the behavior of your body's own protective molecules, suggesting that nature's original design was remarkably close to optimal. Looking toward the future, the convergence of antibody science with other advancing technologies promises developments that seem almost magical. Imagine antibodies that can be programmed to activate only under specific conditions, providing treatments that turn themselves on precisely when and where they're needed. Picture diagnostic tests so sensitive they can detect diseases years before symptoms appear, allowing for preventive treatments that stop illness before it starts. Consider the possibility of personalized antibody treatments, tailored not just to specific diseases, but to individual patients' unique biological characteristics. These treatments might take into account your genetic makeup, your immune system history, even your lifestyle and environmental exposures, creating therapies that are optimized for your particular biological circumstances. The integration of artificial intelligence into antibody development is accelerating these possibilities, allowing scientists to predict which antibody designs will be most effective and to identify potential problems before they occur. Machine learning algorithms can now design antibodies with capabilities that surpass those found in nature, creating molecular tools with enhanced specificity, improved stability, and novel functions. Yet for all these technological advances, perhaps the most profound aspect of antibody science remains the simple fact that these remarkable systems exist at all. The idea that your body maintains a vast library of potential responses to threats it has never encountered, that it can learn and remember and adapt its defenses over a lifetime, that it can distinguish between countless different molecular signatures with perfect accuracy, all of this seems almost too sophisticated to be real, yet it operates within you every moment of every day. The antibodies that protect you represent a kind of biological poetry, written in the language of molecular shapes and chemical affinities. Each one is a sonnet of specificity, a haiku of recognition, a love letter from evolution to the precious cargo of life it has been tasked with protecting. They embody both the fierce protectiveness of a parent and the gentle patience of a gardener, capable of violence when necessary, yet preferring the quiet maintenance of health over the drama of disease. As you settle more deeply into the approaching embrace of sleep, perhaps you can sense in some subtle way the vast protective presence that surrounds you. Not a single overwhelming force, but millions upon millions of individual guardians, each one small beyond imagining, yet collectively capable of defending you against threats that could overwhelm the mightiest fortress. There's something profoundly comforting about knowing that this protection operates independently of your conscious mind. You don't need to remember to activate your immune defenses when you encounter a threat. Don't need to consciously coordinate responses between different parts of your body. Don't need to worry about maintaining the delicate balance between protection and tolerance that keeps you healthy. All of this happens automatically, guided by principles encoded in your genes and refined by a lifetime of experience. The antibodies working within you tonight will continue their vigilant patrol long after you've drifted off to sleep. They'll be there when you wake in the morning, ready for whatever challenges the new day might bring. They'll adapt and adjust as needed, learn from new experiences, and maintain their protective watch through all the seasons of your life. In the grand story of life on Earth, antibodies represent one of evolution's most elegant solutions to the fundamental challenge of survival in a world full of potential threats. They are both ancient and modern, simple in their basic structure, yet capable of almost infinite variety in their specific functions. They connect you to the deep history of life, while providing protection for your unique individual existence. The gentle rhythm of your breathing as you listen to these words is carrying these molecular defenders throughout your body right now, delivering them to every tissue and organ where they maintain their quiet vigil. With each heartbeat, millions of antibodies flow through your circulatory system like microscopic patrol boats, scanning for trouble while allowing the peaceful commerce of life to proceed undisturbed. So as we come to the gentle close of our journey through the remarkable world of your body's tiny defenders, let's take one final moment to appreciate the quiet miracle that surrounds you. The antibodies we've explored tonight aren't just biological molecules, they're the embodiment of life's deepest wisdom, a testament to the extraordinary lengths that evolution will go to protect the precious spark of consciousness that you represent. As you rest there in the gathering stillness, perhaps feeling sleep beginning to wrap around you like a soft blanket, remember that you carry within yourself a legacy that stretches back through millions of years. Every antibody flowing through your bloodstream tonight is descended from molecular ancestors that once protected the first complex life forms in ancient seas. They've been refined and perfected across countless generations, shaped by challenges that would have destroyed lesser designs, emerging as some of the most sophisticated molecular machines ever created. The story of antibodies is ultimately a story about hope, the biological hope that life can persist, can adapt, can overcome whatever obstacles the world presents. Your immune system doesn't know what threats tomorrow might bring, yet it maintains its readiness with unwavering optimism, preparing for challenges that may never come while standing ready to meet those that do. This quiet confidence that permeates your antibody system speaks to something profound about life itself. In a universe that can seem chaotic and unpredictable, these molecular guardians represent order, purpose, and an almost touching faith in the value of the life they protect. They work without recognition or reward, asking nothing in return except the continuation of the biological story they've been entrusted to preserve. And perhaps that's the most beautiful aspect of all that within you, right now, exists this vast community of protectors who have dedicated their entire molecular existence to your well-being. They don't know your dreams or your fears, your hopes or your sorrows, yet they guard them all with equal devotion. In their simple but profound way, they embody the deepest values of care, protection, and service. So sleep well tonight, dear listener, knowing that you are watched over by guardians more numerous than the stars, more devoted than any human protector could ever be. Let your thoughts drift away on the gentle current of approaching dreams, carried by the knowledge that you are part of something vast and wonderful, a biological symphony that has been playing for millions of years and will continue long after we're gone. Wherever you are in this wide world, whatever time it is in your corner of the night, thank you for joining me on this gentle exploration of life's hidden marvels. If this quiet journey has brought you any measure of peace or wonder, please consider sharing it with others who might need a moment of calm in their own lives. Until we meet again in another corner of science's gentle mysteries, Sleep peacefully, dream sweetly, and rest in the knowledge that you are protected, you are valued, and you are part of the most extraordinary story ever told, the story of life itself, written in molecules and told in the language of hope. Good night.